December 27th, 2004. Astronomers detected something that should have been impossible. A burst of energy, traveling for 50,000 years across space, slammed into Earth's atmosphere. In 0.2 of a second, it released more energy than our Sun produces in 250,000 years. Earth's ionosphere, our protective magnetic shield, compressed. Satellites went haywire. Radio communications across the entire planet were disrupted. The source? A stellar corpse the size of Manhattan, 50,000 light-years away. If this object had been just 10 light-years from Earth, not even close by cosmic standards, it would have triggered a mass extinction event. Our atmosphere would have been stripped away. This wasn't a black hole. It wasn't a supernova. It was something far stranger. A magnetar, the most magnetic objects in the universe, and potentially the most dangerous. Today we're going deep into the physics of these cosmic monsters, what they are, how they're born, and what would happen if you ever got close to one. Because understanding magnetars means understanding the absolute limits of physics itself. Let's begin. So, what exactly is a magnetar? Let's start with the basics. A magnetar is a type of neutron star, but not just any neutron star. It's a neutron star that's been cranked up to 11, wrapped in the most powerful magnetic field we know of in the universe. To understand how extreme that is, we need some perspective. Imagine taking our Sun, a ball of plasma nearly 1.4 million kilometers across, and compressing all of that mass down to the size of a city. We're talking about Manhattan, maybe 20 kilometers across. That's a neutron star. The density is incomprehensible. A single teaspoon of neutron star material would weigh about 10 million tons. That's the weight of nearly 2,000 Great Pyramids of Giza in a teaspoon. Now here's where magnetars become truly terrifying. Take that already extreme object and wrap it in a magnetic field a quadrillion times stronger than a refrigerator magnet. That's a 1 with 15 zeros after it. A trillion times more powerful than Earth's magnetic field. How strong is that? Strong enough that if a magnetar existed halfway between Earth and the Moon, about 200,000 kilometers away, it would erase every piece of magnetic data on the planet. Credit cards, hard drives, bank records, gone, instantly. And remember, we're talking about objects only 20 kilometers across. You could fit one inside the city limits of Los Angeles. So why do these things exist? What creates magnetic fields this absurdly powerful? That's where things get interesting, because magnetars aren't just born, they're forged in one of the most violent events in the cosmos, and only under very specific, very rare conditions. Out of the hundreds of millions of neutron stars we estimate exist in our galaxy, we've only confirmed about 30 magnetars. They're rare, they're extreme, and they represent physics operating at the absolute edge of what's possible. That magnetic field, it doesn't last forever. It decays within about 10,000 years, a blink of an eye in cosmic terms. A magnetar burns out and becomes a regular neutron star. But during those 10,000 years, they're the universe's most powerful particle accelerators, gamma-ray cannons, and cosmic wildcards all rolled into one. So now you know what they are, but how does something this extreme come into existence? To answer that, we need to witness the death of a massive star and the birth of a monster. Every magnetar begins the same way, with the death of a giant. We're talking about stars at least 8 to 10 times more massive than our Sun. These are the cosmic heavyweights. Stars that live fast, burn bright, and die young. For millions of years, these stars wage a constant battle against their own gravity. Nuclear fusion in their cores produces outward pressure, fighting back against the crushing weight trying to collapse them inward. But eventually, they run out of fuel. And when they do, gravity wins. The core collapses in less than a second, material falling inward at nearly a quarter the speed of light. Electrons are crushed into protons, forming neutrons. The outer layers rebound off this incredibly dense core and explode outward. A supernova, one of the most energetic events in the universe. For a few weeks, this single dying star can outshine an entire galaxy of hundreds of billions of stars. But we're not here for the explosion. We're here for what's left behind. That collapsed core is a newborn neutron star. Most of the time, that's where the story ends. You get a rapidly spinning neutron star, maybe a pulsar, and it gradually slows down over millions of years. But sometimes, rarely, something different happens. If the conditions are just right, you get a magnetar. Here's what needs to happen. First, the collapsing core must be rotating extremely fast. We're talking about something spinning hundreds of times per second, maybe even 1,000 times per second in those first moments. Second, the newborn neutron star needs to have intense convection happening in its outer layers. Hot material rising, cool material sinking, violent churning motion. When you combine rapid rotation with convection in an electrically conductive fluid, and remember, the material inside a neutron star is essentially a superfluid of neutrons and a superconducting sea of protons, you create a dynamo effect. Think of it like a cosmic generator. The rotation and convection twist and amplify magnetic fields, feeding energy back into themselves, growing stronger and stronger. Within the first 10 to 20 seconds after the core collapse, the magnetic field explodes in strength. From something comparable to a regular neutron star, already 1 trillion times Earth's field, to something 1,000 times stronger still. We're now at magnetic field strengths of 10 to the 15th Gauss. That's 1 quadrillion times stronger than Earth's magnetic field. And here's the terrifying part. All of this happens in less time than it takes you to tie your shoes. 20 seconds. That's all it takes to create the most magnetic object in the universe. But the violence doesn't end there. Because that newborn magnetar, it's not stable, not even close. That magnetic field is so intense it actually distorts the shape of the star itself. It creates enormous internal stresses. The crust of the neutron star, a crystalline lattice of iron nuclei 1 billion times stronger than steel, is being constantly twisted and stressed by those magnetic forces. Eventually, something has to give. And when it does, we get starquakes, we get gamma ray bursts, we get the kind of violent outbursts that can be detected from 50,000 light years away. December 27th, 2004. Let's return to where we started. 50,000 light years away, in the constellation Sagittarius, something happened to a magnetar designated SGR 1806-20. The crust fractured, just a tiny crack. The magnetic field lines anchored in that crust suddenly shifted. They reconfigured. And in doing so, they released an amount of energy that defies comprehension. In 0.2 of a second, this event released more energy than our sun will produce in the next 250,000 years. The burst of gamma rays and X-rays traveled across the galaxy at the speed of light. When it reached Earth, 50,000 years later, It was still powerful enough to ionize our upper atmosphere from 50,000 light-years away. Satellites detected it. The Swift satellite was temporarily blinded. The RHESSI Solar Observatory recorded the most intense gamma-ray flux ever measured. Even instruments not designed to detect gamma rays picked it up. Radio operators around the world reported disruptions. The Earth's ionosphere, the layer that reflects radio waves, was suddenly compressed on the day side of the planet by the sheer intensity of the radiation. If SGR 1806-20 had been just 10 light-years away, the radiation would have been intense enough to trigger a mass extinction. Our ozone layer would have been destroyed. The surface of Earth would have been bathed in lethal radiation. At 1 light-year away, it would have delivered more energy to Earth than standing at ground zero of a nuclear detonation. This is what a starquake can do. The energy manifests as a giant flare, an eruption of gamma rays and X-rays that bursts out from the Magnetar's surface. But it doesn't stop there. The shifting magnetic field also accelerates charged particles to nearly the speed of light. These particles spiral along the magnetic field lines, producing what's called synchrotron radiation. More X-rays, more gamma rays. And here's where things get really interesting. Some of that energy goes into generating seismic waves inside the neutron star. The entire star starts ringing like a bell, oscillating at frequencies of hundreds of hertz. We can actually detect these oscillations from Earth. By analysing the pulsations in the X-ray emission following a giant flare, astronomers can study the internal structure of the Magnetar. It's like using earthquakes to study Earth's interior, except we're doing it for an object 50,000 light-years away. Now, here's where magnetars connect to one of the biggest mysteries in modern astronomy: fast radio bursts. Fast radio bursts are intense pulses of radio waves that last just milliseconds. They come from distant galaxies, and until recently, we had no idea what caused them. In April 2020, a magnetar in our own galaxy, SGR 1935+2154, produced a burst of radio waves coinciding with an X-ray flare. This was the first time we'd ever detected radio waves from a magnetar flare. This was a smoking gun. Magnetars, or at least some magnetars under some conditions, are producing fast radio bursts. It's still an active area of research. Not all FRBs can be explained by magnetars. Some repeat in patterns that don't quite fit, but it's opened up an entirely new way of studying these objects. Now, you might be wondering, do these starquakes happen often? The answer is, it depends. Young magnetars, those less than 10,000 years old, are the most active. They might have giant flares every few decades, smaller bursts every few years, and constant smaller outbursts. But as a magnetar ages, its magnetic field gradually decays. The universe's most dangerous objects have an expiration date. But let's get personal for a moment. We've talked about what these objects can do from thousands of light years away. What would happen if you actually tried to approach one? Let's run that experiment, at least in theory. Imagine you're in a spacecraft. Somehow, you've located a magnetar and you're approaching it. Let's walk through what would happen at different distances. At 1,000 light years away, you're still well outside any danger zone. The magnetar looks like a point of light, maybe pulsing if it's going through an active phase, emitting X-rays and gamma rays. If it produces a giant flare while you're observing, you'd see an incredible light show. Your instruments would detect the gamma rays, but at this distance, you're safe. The intensity has decreased enough that it's just a spectacular spectacular cosmic event. At 1,000 kilometers away, now things get serious. At this distance, the magnetic field strength is reaching levels that affect the fundamental properties of atoms. We're talking about 10 to the 11th Gauss, 100 billion times Earth's magnetic field. Here's what that does. It distorts electron orbitals. Atoms become elongated. Chemical bonds break down. The chemistry that makes up your body, it stops working. You wouldn't just die. Your body would cease to function at a molecular level. And we haven't even mentioned the X-rays. A magnetar at this distance is bombarding you with enough high-energy radiation to vaporize any known material. Your spacecraft, assuming it's made of conventional matter, wouldn't fare any better. At 10 kilometers away, the magnetic field strength is now approaching 10 to the 15th Gauss. At this level, the magnetic field energy density exceeds the mass energy density of normal matter. What does that mean? It means the magnetic field is warping space-time more than matter itself would. If you could somehow exist at this distance, and you absolutely couldn't, you would be experiencing gravitational time dilation and magnetic effects on space-time geometry simultaneously. At the surface of a magnetar, we're beyond the realm of physics we can properly describe. Magnetic field strength, 10 to the 15th Gauss. Temperature, 10 million degrees. Gravity, 200 billion times Earth's surface gravity. A single cubic centimeter of matter here weighs 1 billion tons. The concept of you doesn't exist here. This is a realm of degenerate matter. Superconducting fluids and magnetic fields powerful enough to make the fundamental forces of nature behave in ways we're still trying to understand. Fortunately, the nearest known magnetar to Earth is about 13,000 light-years away. The odds of one forming nearby or one wandering into our neighborhood are astronomically small, but they do exist out there. 30 that we know of. Probably thousands more we haven't detected yet. Silent, spinning, magnetic monsters scattered throughout the galaxy. So how do magnetars stack up against other cosmic threats? Are they really the most dangerous objects in the universe? Let's find out. So we've established that magnetars are terrifying, but the universe is full of dangerous objects. Black holes, supernovae, quasars, gamma-ray bursts. How do magnetars actually compare? Are they really the most dangerous objects out there? Let's run through the cosmic threat assessment. Magnetars versus black holes. Black holes get all the press. They're the universe's ultimate gravitational monsters. Objects so dense that not even light can escape. But here's the thing. Black holes are actually pretty predictable. If you know where one is and you maintain a safe distance, you're fine. The danger zone is well defined. Stay outside the event horizon and you can orbit a black hole indefinitely. Magnetars are unpredictable. A magnetar could be quiet for years, then suddenly unleash a flare with zero warning. That unpredictability makes them uniquely dangerous. Also, black holes don't reach out and affect you from thousands of light years away. A magnetar flare can. SGR 1806-20 proved that. Magnetars versus supernovae. Supernovae are one-time events, catastrophic but brief. A massive star explodes, releases enormous energy, and it's done. The danger zone for a supernova is about 30 to 50 light years. If one went off that close to Earth, we'd be in serious trouble. But supernovae are predictable. We can see which stars are candidates. We know roughly when they might explode, give or take a few thousand years. Magnetars, on the other hand, can produce multiple giant flares throughout their lifetime. They're like supernovae that keep going off over and over for 10,000 years. Magnetars versus quasars. Quasars are supermassive black holes actively feeding on matter, producing jets of particles and radiation that can extend for millions of light years. They're the most energetic sustained phenomena in the universe. A single quasar can output more energy than 1 trillion suns. But, and this is important, quasars are far away. The nearest known quasar is still hundreds of millions of light years from Earth. They're early universe objects, remnants of a more violent cosmic era. Magnetars exist in our galaxy right now, within thousands of light years. Proximity matters. Magnetars versus gamma-ray bursts. Now this is the real competition. Gamma-ray bursts are the most energetic explosions in the universe since the Big Bang. They're thought to be produced either by colliding neutron stars or by hypernovae, supernovae on steroids. A GRB pointed at Earth from within our galaxy could cause a mass extinction. The leading theory for the Ordovician extinction event, about 450 million years ago, is that a nearby gamma-ray burst sterilized half the planet. GRBs release their energy in narrow jets, typically lasting seconds to minutes. If you're in the beam, you're done. If you're not, you're safe. Magnetar giant flares are less energetic than the most powerful GRBs, but they're more common and less directional. The 2004 SGR event wasn't even aimed directly at us, and it still affected Earth. So where does that leave us? Black holes, quasars, and other exotic objects are dangerous, but they're either far away, predictable, or both. Magnetars are nearby, unpredictable, and capable of affecting us from distances we previously thought were safe. They're also rare enough that we don't need to lose sleep over them, but common enough that they represent a real, if small, statistical risk over cosmic timescales. If you enjoyed this deep dive into magnetars, do me a favor, hit that like button. It genuinely helps more people discover content like this. And if you want to see more videos exploring the universe's most extreme objects and phenomena, subscribe and hit the notification bell. I've got videos planned on neutron star collisions, the physics of black hole jets, and what happens inside a black hole. Drop a comment and let me know what keeps you up at night wondering about the universe. And thanks for watching.